Alright friends, here's a video for us to go over the derivatives for sine function and cosine function and tangent function. So, if you remember, a derivative is a measure of slope. Okay? Slope at one point. It's the function that gives the slope at any one point on a curve. And one of the things we can do to sort of see how to best model the slopes of the sine is to pick some points along the sine curve and talk about the slope of the sine curve at those points. Okay? So, a couple points easy to see if we were doing little tangent lines to the sine curve at pi over 2. A tangent line I would draw would be horizontal, would have a slope of 0. Okay? And same thing at 3 pi over 2. So pi over 2, slope equals 0, 3 pi over 2, slope equals 0. I'm going to graph those slopes. And I know there's some weird points on this graph. So pi over 2, 0, 3 pi over 2, 0. Now, I'm going to ask you to kind of go sort of along with me on sort of an assumption. If this slope, the slope at 0, if we consider that a slope of 1, so at 0, slope equals 1, then 2 pi would be the same slope, right? Because of the sinusoidal, the repeating nature of the sine curve. And then at pi, we would have essentially the opposite slope of -1. And so if I can agree that that pattern makes sense, and I sketch a graph or connect those slopes, I can see that when I graph or model the slopes of sine, I end up with a cosine. And that is in fact the relationship that does exist. If I want to write the derivative of a sine function, the cosine function is going to represent that derivative. And if we expend this to a little bit of chain rule, the derivative of the sine of u would be equal to the cosine of u times the derivative of u. So long story short, derivative of sine is cosine. Now, if we do something similar with a cosine function, and I pull those 0 slopes first, and that's kind of, I had these points already planned out right there, the 0 slopes. So cosine has a 0 slope at 0, cosine has a 0 slope at pi, cosine has a 0 slope at 2 pi. If I agree that that is a -1 slope, which would make that a +1 slope, then I get that, horribly graphed. And that is in fact the opposite, or a negative sine function. And so once again, the rule is, and with the chain rule part included, that when I take the derivative of a cosine of u, I'm going to get negative sine of u times du. Or derivative of cosine is negative sine, or the opposite of the sine. Two very easy rules to memorize. Derivative of sine of cosine is cosine, derivative of cosine is negative sine. Another way, there's like a little device here. If S stands for sine and C stands for cosine, wherever I start, one step down is a derivative. So if I start at sine, one step down, derivative of sine is cosine. If I start at cosine, one step down, derivative of cosine is negative sine. And then the nice thing is, it kind of can continue. So if you started with a negative sine, your derivative would be negative cosine. If you started with a negative cosine, your derivative would be positive sine. That's my little trick that kind of helps me when I'm doing my derivatives for sine and cosine, because it's easy. You know you're going to go back and forth between sine and cosine. Sometimes the negatives get confusing, especially when you have a negative cosine. The fact that the derivative ends up being a positive sine sometimes takes some thinking. But this little chain kind of helps you keep them straight. All right, so now that we know that the derivative of sine is cosine, and the derivative of cosine is negative sine, let's figure out what the derivative of tangent is. So let's just talk about tangent of x and rewrite that as the sine of x over the cosine of x. If I decide to take the derivative of this sine over cosine using the quotient rule, here I go. I'll take my denominator times the derivative of my numerator. Right, so this is f and this is g. If f is sine, f prime would be cosine. If g is cosine, g prime would be negative sine. So I've got g f prime minus, f g prime, gf prime, fg prime over g squared. Now this is a fun combination. I love this because it uses a couple different identities. First of all, cosine times a cosine is a cosine squared. And I'm going to decide to write it like that. A sine times a negative sine is a negative sine squared, but behind a subtraction is going to become a plus. Now, before you pull out bad algebra and cross things off here, pay attention to the numerator. You can't divide out those cosines as much as you want to. That's not algebraically legal. But what you can do is you can replace sine squared plus cosine squared with 1. And 1 over cosine squared is a secant squared. And so, if I want to write it, I can write it a couple different ways. The third rule that we'll need to know is that when you take the derivative of the tangent, you're going to get a secant function, but you're going to get the secant function quantity squared. That's not obvious. We could look at graphs to kind of show how the slope of the tangent is modeled by the secant, but we don't have a good handle on the graphs of tangents and secants, so I don't know that that's going to mean a lot for us, not the same way that sines and cosines can. But this nice little quotient rule activity with sine over cosine, if you buy the derivatives of sine and cosine working the way they work, it leads really nicely to show how algebraically the derivative of the tangent ends up as the secant squared. And there's all 6 trig derivatives. Like I said, these are the 3 that we primarily focus on because they're the most useful in terms of modeling. But you've got, for all 6 trig functions, the way their derivatives can be represented. And you can show the other 3 derivatives using a same kind of idea with identities and some quotient rules or some chain rules to show how these would develop. All right, I'm going to pause there for a second, and in our next part of the video we're going to go ahead and do some practice problems. Okay, so I took a little pause. And now we're back, and we're looking at some practice problems that involve taking the derivative using sines and cosines and tangents. And if we want to make some notes, if we want to remember our sine, cosine, negative cosine, sine, little strand to help us keep track of our derivatives, going from sine to cosine and cosines to sine. And then kind of as a separate one, the tangent ends up as the secant squared. So, first things first, a constant times a trig function. When we take the derivative, you don't need a product rule with a constant. A constant times a trig function, the constant basically kind of comes along for the ride. So when I have 2 times the sine of x, the derivative of that is going to be 2 times the derivative of sine, which is cosine of x. Following that same logic, we can write the derivative of number 2 as negative 3 times negative sine x, or positive 3 sine x. Now you could think about that a couple different ways. You can do like I did and say, okay, I have a negative 3 and then the derivative of cosine is negative sine. Or you can kind of think of that all together as, well, this is a negative cosine, like right here on my chart. And so the result I'm going to get is a positive sine. Just kind of have to pick which way works best for you in terms of understanding it. Sums and differences of trig functions, treat them individually, just like sums and differences when we had polynomials. Oops, I don't want to write in yellow. Oops, and I don't want to not erase. Oh, good Lord, yes. I love it when okay, so y prime here would be, well, it's a cosine, so the derivative is negative sine. So negative 5 sine x plus 4 cosine x. And if we've got mixtures of trig functions and polynomial pieces with adding and subtracting, we can treat those pieces separately. So the derivative of the 2x is 2, and the derivative of negative 2 cosine is going to be plus 2 sine x. Similar thing down on number 8. The derivative here of the root x is 1/2 x to the negative 1/2. And then the derivative of 4 cosine is negative 4 sine x. In problems 4, 5, 6, and 9, we've got a little bit of product rule. On 4 and 6 and 9, all of those have product rule. And then problem number 5 has a little quotient rule. So why don't you go ahead, if you want to pause right now, and try a little product rule on number 4, a little product rule on 6 and 9, a little quotient rule on 5, and then you could check your answers. For me on problem number 4, if f is x squared, then f prime is 2x. G is sine, so g prime would be cosine. So when I use my product rule, it's going to be sine of x times 2x. That's gf prime plus f, x squared, times g prime. Now the argument of the trig function doesn't get affected by multiplying by other x's, so this x here and this x here isn't going to change with that 2x and that x squared. So sometimes I would prefer to write the 2x in the front, so 2x times sine x plus x squared cosine x. Even though that's not technically gf prime plus fg prime, it just makes a little sense to have the polynomial chunk in front of the trig chunk for me, so that the argument of the trig doesn't look like you can change it. Sometimes it says something behind it, it looks like you're allowed to change it. So cosine times cosine. Okay, so because if f is sine, f prime is cosine. So this is gf prime plus f, and then g prime. So this is going to be a cosine x quantity squared minus a sine x quantity squared. If you want to stop the video now and kind of go forward to the last part where I'm going to do some problems on the back, you can. Or you can hang tight here. I'm going to do these 2 quotient rules. So it's sine of x times 5 minus 5x times cosine x over sine x quantity squared. That's my little quotient rule number 5. And then number 9, another product rule. Tangent of x times 3 plus 3x secant squared x. Okay, I'm gonna stop this one now, and then I'll do a second video where we do some problems on the back with chain rule.